Okay, welcome to the Rustacean Station. My name is Jeremy, and I'm one of the editors and other hosts on the Rustacean Station here. Today I'm joined by Dr. Christoph Zimmermann, who is a solution architect at Redis-Labs and also has a PhD in reflective OS design, which I definitely want to ask about. He's a board member of miscellaneous sort of Linux things, and he's here today to talk to us about a new project from Redis-Labs, specifically RedisJSON. Who are you, Christoph? Tell us a little bit about yourself.
Yeah. First of all, hi, Jeremy. Thanks for having me on the show. And before we continue, drop the doctor. PhD, doing a PhD is nice, but normally that has a medical connotation associated with it. I get asked about what can you do about my flu? I have a broken leg. Can you fix it? That sort of thing. No, it's so Chris is okay. I'm a PhD by training. I did actually my PhD on something called an experimental microkernel architecture back in 1990 when I submitted a thesis at a university called Trinity College Dublin. As the research team, we developed a microkernel architecture comparable at the time to something like Mark III, which is actually close to something that Microsoft called NT because quite a few people went there. I think the other half went to Apple.
Okay.
Doing something called what is now OS X. As a next step. So the idea was, at the time, before I diverge too much, the idea was to construct a kernel that was opening certain mechanisms in a very controlled fashion to applications so that applications could reconfigure the behavior of these subsystems at runtime. So in contrast to the then prominent approach, i.e. the operating system basically does tell the application what to do, it was the other way around. And I wrote actually the meta-level architecture for this, something that later made its way into something called the Reflection API as part of the JDK 1.5. I wouldn't say they took it literally as in James Gosling and Friends, but the concepts are pretty similar. Unfortunately, I didn't patent the IPs, so I still have to work for a living instead of sitting on my Caribbean island powered by Oracle. So
how did you get into open source then, obviously?
Actually, I started open source even before I did that PhD. I compiled my first version of Emacs on a Sun Solaris box in 87. That was the first point in time when I came across the notion of open source. And we developed the microkernel architecture back in the day just using open source as a tool chain, if you will. And that was also the first point in time around 93, 94, when I stumbled across something called Linux.
Yes, yep.
Which has been accompanying me ever since, more or less. Because we were looking for a test system that we would use in order to develop and QA the kernel, the microkernel architecture. So we came across Python because that's what we used then. In order to write much of the QA framework. And I've been stuck with open source, for want of a better expression, ever since.
Well, I guess it makes sense that why you ended up at Redis then, being that they're pretty big on open source, and for everybody who's into databases and things like that, they'll definitely know the name, at least of Redis. You recently did a FOSDEM talk about RedisJSON, and obviously that's why we wanted to have you on today, because this new Redis module is written in Rust, which is presumably a first, to our knowledge at least. So obviously we should talk quite a lot about that. But firstly, for anyone who doesn't exactly know what Redis is or what an in-memory database is useful for, could you give a quick explanation about what that is?
Before I do this, one important differentiation. Redis-Labs, home of Redis, is the company behind Redis, and Redis is the open source project. Just to get this right, because there are quite a few service providers that offer Redis. The hyperscalers come to mind, but only Redis-Labs is actually where the development of the project takes place. Some of the funding for the code base comes from all the rest of it. So let me shed some light on the history of Redis.
Yes, please.
And also to some extent without doing too much commercial promotions here on Redis-Labs. But about 10 years ago, an Italian developer by the name of Salvatore Sanfilippo was looking for a performant database with certain real-time aspects for a web reporting project. He took a look at Memcached, he took a look at Postgres, he took a look at MySQL, but none of these projects were able to satisfy his real-time requirements. So he ended up writing his own what was then a key value store. The first commit took place, I think, on the 21st of March. Wasn't even on GitHub then, but somewhere else. Before he basically took the code base from that platform to GitHub. And over the years, quite a few data structures came to the original key value association, because Redis started out as a binary safe key value store, pretty similar to the functionality of the early Memcached versions. Another popular key value store, I might add. But over the years, data structures have entered the code base like sets, like sorted sets, as an ability to associate a score with set items, bit fields, lists, being probably the abstraction that can be found in quite a few programming languages, in addition to something called streams, which essentially are scalable message bursts.
What's a scalable message burst?
Something similar to RabbitMQ, maybe in the commercial world MQ series, or something called Kafka, also backed by a company called Confluent. The idea is to have message processing in main memory. So where Kafka basically use partitions residing on disks and other means, streams do it in main memory. With the same abstractions like consumer groups and so forth. So that gives you a scalable infrastructure for your real-time requirements.
When you say in main memory for this application, you're obviously imagining that all of the heavy lifting in the compute is being done on some sort of server somewhere. So for main memory, does this mean the RAM of the server specifically on a hardware level, and that's the explanation for why it's so performant? Or is it a hybridization of something like RAM with maybe cheaper sort of storage on the server end, like SSDs, that sort of thing?
You hit the nail on the head. That's exactly how it works. The idea behind the original implementation was not to store data on this. Persistence is offered but came later, but rather to do all the processing in main memory, where other databases like the traditional SQL-based ones would store the data on this and then having to retrieve it and so forth. Redis does it all in main memory. And that gives this performance where Redis, as a NoSQL database, probably the leading NoSQL database in the area of main memory of real-time computing, really shines.
In terms of the performance delta between one of the persistent ones versus one of the in-memory ones that you were just mentioning now, is that a relatively similar performance delta to that as if you just compared the raw hardware? For example, maybe you're getting tens of gigabits per second out of RAM, single-digit gigabits out of a very modern SSD, and then maybe about a tenth of that if you were to go to a traditional magnetic spinning drive? Or is it, once you move it into this database format with Redis or something, is it relatively sort of a power of 10 or 20 every time you change hardware, and therefore the in-memory representation, or is it something else?
No, I mean, it's similar to the first comparison delta that you mentioned, in terms of, because if you stick to main memory, all this overhead of first storing data on disk, then forgetting about it because the OS preempts this main memory as part of their virtual storage memory management, and then having to get the data back from disk is pretty comparable. Traditional SQL databases have come some way, let's put it this way, in terms of intelligent caching, but imagine a database that only does caching without having to go through to the disk at any stage, and then you have it. Redis offers persistence, as I said, but this is optional and it has to be configured separately.
So naturally, if you want something to be super fast and super performant, like I imagine a lot of people who target the learning Rust as a language want, Redis seems like a reasonably logical choice without being too commercial in the push there.
Yes, going back to the history of the project, Redislabs was set up in 2012 with the idea of offering Redis as a service. Then Salvatore joined Redislabs, I think, in 2014, 2015. So that was the point in time when the project lead joined Redislabs, has been with the company ever since. You'll see this actually for example, in the GitHub commits. Many of the contributions, many of the commits, for example, of the modules, and RedisJSON 2 would be one of them, come from Redislabs. So Redislabs, the entity behind Redis, funds the development of the native server code base, but also much of the ecosystem surrounding it. So quite a few commits of the standard Java clients for Redis come from, for example, from Redislabs.
That's fantastic that he's been able to join the project again after this time. You mentioned modules just now. So what's a Redis module?
Redis modules came into existence, I think, about 4 years ago, 5 years ago. The idea was that although the data structures offered by native Redis are quite comprehensive, as I said in the beginning. Application programmers requested additional functionality. That's probably the best way to do it, of how to describe this. In terms of, okay, we have these native data types, but what we really want, in addition to these, is, for example, a graph database, or is a document database, or is a time series database, with the same performance metrics offered by native Redis, i.e. the ability, for example, to store and to retrieve a graph in main memory rather than on disk, like the other graph databases normally do it. A module from a technical perspective is an extension on the server side, which you have to load during the server startup phase. So you pull down the code from GitHub for Redis, compile it, then that gives you native Redis out of the box on your operating system of choice. Separately, you pull down the module source code, you compile this, that gives you something comparable to a shared object to stick with the Linux parlor. And you will then load this shared object as part of the server startup based on your particular configuration. After that, you have additional data types at your disposal representing graphs and so forth. These low-level commands are great, but most of the time this is not something that the application programmers are looking for, the developers. More often than not, these modules are accompanied by client-side implementations comparable to other client-side implementations that are able to look after native Redis commands.
So another layer of abstraction to help the developer just be more effective and be more productive.
Exactly, that's exactly it. If you take a look at Redis.io, you'll find that Redis natively supports about 50 programming languages with more than 160 client-side implementations for the native data types.
So just a few.
Just a few, not that many, no. On top of these, you get, as I said, module-specific language bindings, but that also have the advantages of, for example, with some modules, implementing industry standards. So, for example, if you take a look at Graph, there has been a graph query language been established more or less as an industry standard called OpenCipher, originally developed by Neo4j, which has but now become more or less the standard for querying and manipulating graphs. So if you take a look at the client-side implementation for Redis Graph, this offers basically OpenCipher compatibility, and this is achieved through proper language binding based on certain programming languages like Java, Python, Golang, and so forth. Only this abstraction in that particular case and others gives you the industry kind of standardization out of the box, which is important because you want to develop applications that maybe can port to other graph databases as well.
Great explanation. In this case, we're not talking about graphs, though. We want to talk about JSON, obviously the JavaScript object notation. So RedisJSON is written in Rust. Let's just start with the obvious question. Why did you do it in Rust?
Okay, RedisJSON 2 is written in Rust. RedisJSON 1 is written in C. Okay, C is the language that the native server is written in.
Okay, so one-to-one between the module and the native.
Exactly. 3-clause BSD, off you go. When Salvatore started to design the module interface, he of course stuck to C because that was the language he knew best and had used at the time for about 5 years to implement the server code base. So that was the natural SDK initially. And you'll see this when you take a look at quite a few of the initial module implementations, like Graph, like Redis Search, like RedisJSON 1. They're all written in C. Two main reasons, because, the SDK was written in C, as in the software development kit, or the API that talks to the server as part of the module specification. And B would be performance, because C natively gives you a pretty good performance, but has a couple of drawbacks that specifically Rust addresses, like memory safety, QA, and so forth. But I'm sure we're going to go into more details on that later on.
Yes, definitely.
So when engineering decided, as in the group who developed RedisJSON 1 inside Redislabs, decided to do a re-implementation, they went for Rust rather than C, RedisJSON 2.
So was the original version, was it a maintenance issue? Was it an opportunity just to try out a new technology on something that you otherwise had a good version that you could always fall back on if there was something wrong? Can you unpack a bit more about the sort of why Rust?
Of course. The RedisJSON module was in for a function overhaul anyway.
Okay.
The C implementation was showing its age, and functional extensions were clearly on the horizon. But also, the team that was in charge of developing this and other modules also wanted to take a look at a newer technology with a couple of traits. For example, less QA effort in terms of, if you take a look at your ordinary C development use, you tend to spend, even if you have a good understanding of how C works internally, you still spend a good amount of time, basically, for example, fixing memory leaks. Yep. Because in C, you all have to do it manually. If you want to have some memory, you ask the operating system, you get back a pointer, and then it's up to you to do with the memory what you want. You can store values in it, you can release it, you can reallocate the whole thing, and so forth. The trouble, of course, starts, for example, if you forget that you actually allocated it and never release it, because in that case, memory will keep piling up. Or worse, you release it, but keep the pointer dangling, and then some other parts of the application tries to access the memory. In a good day, you get back false data. On a bad day, you actually get a segmentation violation because you're trying to access a memory segment that is no longer valid as part of the page table of the corresponding application. On a really bad day, you get something called an increase of the attack surface because you have a dangling pointer.
I've heard this before. Increase of the attack surface.
The attack surface is basically how you can break an application. So if you manage to tweak a pointer, or if you encounter an invalid pointer that points to something that is no longer in existence, you may be able, if you know how this works internally, to exploit this fact.
Yes, okay. So potential attack vector there by not managing the memory correctly.
And that, of course, contributes to the overall attack surface of an application. So, and that was the reason why they deliberately checked out quite a few languages and stuck with Rust, and then did the first implementation of RedisJSON 2 in Rust. And I don't know if you've heard this before, but there's a saying in the community that in contrast to other programming languages, if you can convince the Rust compiler to generate code, you're almost there. because this is exactly what Rust does. It takes apart your source code, checks it out thoroughly, and puts it back together again.
Yes.
The effort that it takes to, for example, verify your handling of memory, concepts like borrowing and the whole ownership of a memory associated with a particular variable comes to mind,
and
including scope checking,
well.
lifetimes, exactly, like scope checking and so forth. So, and this is, I think, one of the main benefits of Rust, because so much is done at compile time. The effort on the QA side, especially at runtime, basically, once you have a build and then you put it through its ordinary QA lifecycle, tends to shrink, depending on the particular code base, quite a lot, as a matter of fact. I mean, I'm not revealing any secrets here. We're not the only ones, as in Redislabs, not the only company seriously taking a look at Rust. I hear it's the latest rage at Microsoft too, for a reason. There was actually a presentation that I recently saw done by one of the chief Microsoft people, who basically took about 30 minutes, 45 minutes of his time to explain why Microsoft is slowly moving away from C++ to Rust.
Memory safety, probably the number one reason if we're talking about the same article, which I think we are.
Exactly. The conclusion, why we took a serious look at Rust going forward.
I want to potentially unpack something that you do just saying there about the debugging issues before runtime at compile time as opposed to runtime, and therefore it's shortening your QA cycle. And probably as a result of that, overall, it makes your engineering team more effective. And I want to give this a bit of a shout and put a bit of a pin in this for a moment, because I think it's something that doesn't get enough attention for Rust. I mean, it's built on these three pillars of safety with a great memory model, concurrency, and speed, i.e. very, very close to C++-ish performance, but without all of the drawbacks of memory management or shredding and any of that. But the specific optimization for developer time is a huge cost to enterprise and industry. And actually, if you've got engineers who are very enthusiastic about wanting to use a new technology, you should try and push them towards Rust, because it will save your company money in if nothing else other than it will make your engineers have to do less hours to get the same output.
Absolutely, I couldn't have said it better. Even if you take a look at your typical what is called Pareto model or something, as in you spend about 20% of the implementation on the implementation of the initial code base, and then 80% your mileage, of course, may vary on ASM, application support and maintenance, i.e., including new features in the code base, fixing bugs, that sort of thing. In Rust, again, that helps you because it supports a very interesting approach to packaging. First of all, the tool chain is great. Plus, I think the namespaces, although quite comparable to other programming languages, help to structure possibly significant code base quite a lot. But similar to, I'm almost tempted to say Java and other programming languages, it does the checking of these at compile time.
Yes.
Rather than at runtime, like the likes of Python and so forth do it. And this is the main benefit, because if you incorporate a new piece of code or a new piece of functionality in your code base, you trigger build, but at the end, should the build conclude successfully, you can put this immediately into QA, which is then kind of a lessened effort, because you can be certain that the compiler basically took the new functionality apart, checked it, and put it back together again, and then concluded it, and then included it in the existing code base. So you'll gain on the QA effort. And especially if you're looking at the life cycle of a project, and especially if you're dealing with a kind of complex project that has been growing over the last couple of years, if not decades, again, Rust basically takes you by the hand and kind of, I'm almost tempted to say, enforces the whole thing, because Rust by itself offers a great QA framework. Unfortunately, RedisJSON 2, for historical reasons, basically didn't avail of it to the extent that the engineers could have done this, but also takes you by the hand with doc strings and general documentation of your code base. So the technical depth that you enter when maintaining code base is lessened, is decreased in comparison to other programming languages, which of course does help with the overall effort you spend on maintaining and extending a code base.
Yeah, and I think there's other things as well in the Rust toolchain other than, for example, cardcode, which is just going to do your build maintenance. But there's also, Rust has a very, very powerful testing framework built into it from scratch. And I'm guessing from the sounds of things that you love to reduce the load on QA. So presumably when you were adding new functionality with each build, you were really heavily leveraging the Rust testing framework?
More and more so, yeah. But for initial reasons, the first rounds of QA were done using the existing Python-based framework, which is mostly focusing on the client side, mainly for historical reasons. But going forward, yes, engineering will increase more and more the test coverage using native Rust tooling.
How have you found Rust as a tool for interacting with other languages?
Funny you mentioned that, because one of the first things that the group implementing RedisJSON 2 had to do was actually to write a crate that would emulate the existing C bindings for the module SDK.
Yep. Lots of unsafe blocks, I guess, in there.
Yes, indeed. But otherwise, you won't be able to interface with the existing code base written in C. So that's okay.
Yep.
Was spent on getting things right, as in trying to keep and you'll see this actually on GitHub when you check out the code base, trying to keep the unsafe blocks to a minimum, so that you would thus lay the foundation for an infrastructure that you can then use going forward to implement more and more code bases in Rust natively.
Mm-hmm. In terms of implementing more things in the future and in general development, there's a bit of a saying in the Rust community of if your code's not working, then you should go to the unsafe blocks immediately. I'm guessing you find that to be accurate?
Depending on the use case. As I said, a lot of time was spent analyzing the existing SDK, the C bindings, and then coming up with a proper design addressing that particular, what's what I'm looking for, transfer of control is probably not picturing it, but basically getting this migration right from a safe code base represented by Rust. From a Rust perspective, unsafe code base, i.e. the language bindings representing the SDK, and ultimately talking to the server. As I said, quite a few hours, if not days, were spent on getting things right there because it's so crucial, because any room for error in this particular layer would then lead to challenges later on with any Rust code base you base on this SDK.
Yes, of course. Has working with Rust and its very opinionated compiler and its ideas about how to do memory management and that sort of thing, do you think that is going to shape the way that you do memory management at the lower level, the existing C implementation right now, the pure Redis that you were talking about before? Do you think Rust might find its way down to that metal?
That would probably mean replacing the existing C-based implementation with Rust of the server side, and that probably won't happen. Mainly driven by the code, by the roadmap. Of the project. If you take a look at the code base as in found on GitHub, you notice that although it may, in comparison to other projects, it may seem compact, but a lot of optimization has been flowing into the C code base already. So I don't see this migrating to Rust or similar languages anytime soon. But the modules are, of course, a different story.
Yep.
And that's exactly what happened, if that makes sense.
That's what's happened with the modules, as a result of the RedisJSON 2 module that you've just done in Rust that we've been talking about. You think other modules might also be done in Rust from here going forward?
There are no concrete plans for the re-implementation of other modules now.
It's okay if you can't say.
No. That's I mean, but let me answer that question that way. Redis-Labs, especially the engineering people, are really taking a very close look at Rust as a strategic choice of language going forward. If we think about a new module, there must be very good reasons for implementing this in C. With the SDK crate, we now have a foundation that is just ideally suited to do any other module implementation, especially if we're talking about a new code base, simply in Rust rather than C. Because the crate is there, it works in production with RedisJSON 2, so it's an established code base. And as I said, the advantages from an engineering perspective for us are clearly there. Although I think the feedback that was obtained from the engineering team and other people I talked to, that Rust is probably not the easiest programming language to learn.
Do you want to talk a bit about the teething issues, maybe when you?
Yeah, I'm not disclosing any secrets here, but I reckon the learning curve in comparison to other languages, Python comes to mind, but also Perl or something. The learning curve with Rust is pretty steep. For
the memory management stuff, lifetimes, borrow checker, that sort of thing, or?
Exactly. These are concepts that totally make sense from Rust perspective, but coming from other programming languages that do not offer that type of support, for want of a better expression, that type of safety, let's put it this way. I mean, Rust starts out with a strong type safety. It starts there, and then it doesn't stop at concepts of lifetime, the borrow checker, the beloved borrow checker, and memory management in general, and so forth. So if you've done C or C++ programming for the last 20 years, you may have quite a steep learning curve grasping the concepts. I wouldn't particularly recommend Rust as the language of choice if you are just starting to learn to program. Because first of all, you have to master the learning curve. In addition to learning programming, that might be a little bit over the top. So
Interesting. I think that I wish I had started with Rust. And the reason is, if you assume the best in the nature of things, and if you assume competence, which I think is reasonable to do some of the time in the engineering world, you might start with a language, for example, maybe you pick one of the easier languages like C# or something like that. And in the process of learning it, you start with simple data types and that sort of thing, and then you move on to more complex data structures, and you move on to complex control flow and those sorts of things. As you're creating all of these mini projects, as you're learning, you are assuming that everything you are compiling is safe, and it's not. And maybe from day one, recognizing that you can be in a situation where you can program something that's dangerous. Like at my company, we work with robots. So if you are messing around and if your program is not good, if your program is not safe, even in a memory capacity, or even it's got undefined behavior or something like that, your code can be very powerful. And maybe having that gravitas is actually something that's probably good for new students.
No, I see your point. On the other side, I mean, if you don't know what a loop is, if you don't know what a variable is, if you don't know what a scope or lifetime is, it may seem overly complex from the outside if you're just starting with the basics, as in programming 101.
In terms of, but I mean, if you hit cargo new and then you just create a binary, for example, you'll get something that does hello world for you instantaneously, right? And then if you're using the right crates, you can have a pretty similar experience to Python. I mean, I'm thinking last week, for some reason, I had to replace an existing Python tool from the operations team, which is not something I usually do, but it was just this thing that checks whether or not the company's website is up and then emails people otherwise. And just thanks to good crates being available, particularly the letter crate, which is not spelled the way that I would spell letter, but it's kind of funny in the way that it's misspelt, and I guess that makes it easier to remember. I actually ended up writing it's almost like a script, but it's not because it's a binary, but it's something like 20 lines of code, whereas the Python one was 60 and had like 5 or 10 different libraries in it. This one is like 20 lines with one library being pulled in. I mean, in some applications where Rust has really saturated and the crate ecosystem is really good, I think you can have a pretty similar experience to a scripting language in a lot of ways. But you are right that you do need to understand loops. At some stage, you have to go through all of these things like control flow or conditionals, et cetera, and learn the art of building a complex behaving program out of very, very simple and easy to understand primitive things, I guess. So, yeah, that's an interesting. It's an interesting debate, I think, whether or not Rust is a good language as the first one. I think we can all agree that it's probably better to learn Rust first than it is to learn assembly.
True. Yes. I mean, programming languages are like, what's the analogy I'm looking for? Like cars or bikes. I mean, they all take you from A to B. They all work similarly. The color may be different. The engine specification may be different. But at the end of the day, you're looking at means for transport. But I wouldn't, for example, recommend a learning driver to get behind the steering wheel of a race car right away.
It's a good point, but what's not a race car? I mean, really? I mean, famously, the Instagram stack is predominantly Python, right? Which is just mind-blowing.
Same was for Dropbox, so I hear.
Yeah. Well, Dropbox have been pretty aggressively moving to Rust. It sounds like maybe they're taking a leaf out of your book. We should maybe move back to the Redis-JSON stuff. What might an application look like if somebody's using Redis-JSON too?
Interesting question, and glad that you asked it, because Redis-JSON is, whether 2 or 1 doesn't matter, is at the end of the day a document-oriented database extension for Redis. Meaning, if you have any sort of document, so comparable to in functionality to the likes of Mongo, of Couchbase, if you have any sort of document to store or to index, you would normally do this using Redis-JSON, because documents, more often than not, are coded in the JavaScript object notation as in JSON itself. So if you are a application programmer, front-end, portal solutions, any applications that require the handling, the indexing, and so forth of documents, especially if encoded in JSON, Redis-JSON is your choice, especially if you look for a performant DocumentDB extension. Being an extension of Redis, it has one particular feature. It does it all in main memory, similar to Redis itself, because that's the focus of this NoSQL database. So any real-time aggregation stuff comes to mind. Also IoT applications or IoT stacks that generate data in either a binary format, which is then translated to JSON, or simply generate JSON natively.
You said performant there. In terms of the new module versus its predecessor, what is there a performance performance delta that's observable? I mean, I've watched your FOSDEM talk, so I know the answer to this question already. But for our listeners, what's the performance delta?
If you're interested in the technical details, yes, check out my FOSDEM talk. Shameless
I'll
plug.
put the link in the description.
Yes, thank you. But funny enough, yes, you do pay a performance overhead, but funny enough, in comparison to the native C stack, it's not that big. So yes, Rust adds a certain performance overhead, but you're not talking orders of magnitude here. You're talking about kind of 1, maybe 2-digit percentages, if at all. At the very benefit to shift much of the effort from runtime testing to compile time builds.
Yeah, well, it would take a very, very, very long time for you to lose all of the time that you would otherwise spend debugging, calling get on all of these values that you've stored in your database, right? If the delta is, milliseconds each time you're calling that data back, then you probably have to call some data trillions and trillions of time to get back an hour of developer time that you've otherwise saved, right?
Yeah. No, I mean, that's exactly it. We were quite aware of the fact that Rust was going to add a certain performance overhead, but we're quite surprised at the low order of magnitude that this was actually the case. You're not looking at an awful lot given the benefits that Rust offers as an implementation language for a module.
I was pursuing a line here of perhaps that there is a small performance overhead, but 1, you can earn it back with developer time, and 2, do you think there's a potential for that overhead to go down if you leverage some of the things that Rust is very good at, for example, concurrency?
Good question. At the moment, I do not see this dropping significantly, but maybe over time with the adding of new features, the performance overhead will shrink in comparison to the complexity that you would have introduced by maintaining the C-based implementation. Because more often than not, additional functionality introduces additional complexity in the code base, meaning that with the more lines of code that you include in the module code base, you also increase the complexity, goes without saying. And I reckon that going forward, C would just introduce more complexity because it's not as concise as Rust. Some of the stuff you get in Rust for free, like the memory management, you have to do in C manually and so forth. So going forward, I would expect that overhead will also further drop that you pay for using Rust. But to the order of magnitude, I do not know.
Like we alluded to earlier, Rust sort of built on these 3 pillars of memory safety and speed and concurrency. Do you think out there, and it might not necessarily be specific to the RedisJSON module, it could be relating to search or it could be relating to graph. Probably actually it would relate more. You could probably get better translations of leveraging Rust's ability to do concurrency very, very well in the spaces of search or in the spaces of the graph stuff. And do you think that's an area of interest for you guys going forward for newer modules or refactoring of modules like we said earlier?
Maybe, and let me give you the rationale behind this maybe. If you take a look at the native server implementation, I'm not talking about modules here, I'm just talking about the server itself. The server has one important trait, it's single-threaded. This is basically where it gains its speed from. And the main disadvantage that you introduce this with this approach is actually client-side blocking in terms of any time that single thread is executing something on the server side, any client side is blocked. Although in version 6, it's slightly more concurrent in terms of parallel, but Salvatore designed this with the intention of not introducing additional complexity, additional kind of runtime performance, but by explicitly making it multi-threaded. So the idea is to have an ultra-fast database engine at your disposal that is single-threaded. If you take a look at the code paths of the code base on GitHub, you'll see that much of the code bases are quite short. As a matter of fact, if you go to redis.io, you'll see the complexity in O of N notation for each and every command that the server offers.
Might it also be just a byproduct of if the first Redis, like you said earlier, I think you said 1987, right? There wasn't exactly a large amount of parallel machines and parallel compute going on that time. Even moving into the 90s, which was the next milestone that you mentioned. Again, do you think it'll move to a massively parallel architecture at some stage in the future?
Very good question. Going back to the single-threaded nature of the original implementation, what quite a few modules, and I think Redis Graph would be the prominent example here, have introduced is a certain confined level of parallelism on the module layer. The modules have most of the time one important trait. They use the data types as offered by the server natively as their foundation for the implementation of their side. So, for example, if you take a look at Redis Search, which is a full-text search engine, much of the data types used by the Redis Search implementation are hashes, something that is offered natively by the server. So if you would introduce additional parallelism on a module base, you would have to synchronize going back to the server-side implementation each and every time you do this. Would introduce additional overhead on the module level because of locking. Simple. So I clearly see parallelism increasing depending on the particular use case. Now, in contrast, Redis Graph is not so much relying on the native server data types because it uses a compact binary format for storing and manipulating the graphs based on GraphBlast, which is an open source library that boils down to the handling of graphs, down to the manipulation of matrices. So it's ultra performant because it can be done on a kind of sparse matrix basis. And that's exactly what GraphBlast is pretty good at. So Redis Graph only use Redis to store and retrieve these compact matrix representations from the engine. So what it does afterwards is basically down to the module implementation. So that's the reason why you can increase parallelism on the module side where it makes sense. And going back to your observation with regards to deploying multiple cores on any given machine, what our community actually does, if they want to have better throughput utilization of their multicore architecture, they simply put a couple of Redis servers, clustered or not, on a single multi-core machine. Meaning each and every core runs its own Redis instantiation.
Because of the CUDA model, in terms of just tons of kernels running that all...
Something along these lines, Redis has a cluster implementation also as part of the open source code base, you can find on GitHub, that allows you to subdivide the key space. And it does so more or less automatically. You still need client-side implementations for this. But from an application perspective, the complexity offered by the cluster is manageable, let's put it this way.
When the customer is spooling up the clusters, you're duplicating the data between all of them, so you have multiple concurrent copies of the data?
Only if you use something called high availability. Okay. There's a center-based approach, but that offers a typical, what's it called these days, primary, because we can't say master-slave anymore because that's not politically correct. So I think
yes, of course.
The latest nomination is something called primaries and replicas or something like this. Don't quote me. Okay. It's on the website, so look it up. It's redis.io. So for each primary, you have at least one replica. Should that primary fail, the cluster management will take care of promoting the replica to a new primary and will also recreate a new replica. But if you do not use Redis in a high availability fashion, Redis as such is a shared nothing architecture, meaning that the key space is actually subdivided into so-called hash slots. And these hash slots, based on a CRC16 computation, subdivide the key space so you know exactly what part of the key space is residing on what cluster node, what cluster instance, let's put it this way.
Interesting. Because another thing that is really underappreciated about Rust is its ability to give very, very easy access to multi-threading for people. I mean, a classic example of this would be perhaps the Rayon crate. I don't know if you're familiar with it, but if you have been programming for like 2 weeks, then you can write your first multi-threaded program with relative ease if you change iter to par iter and bring in the Rayon crate. I don't know if other beginners in Rust can remember their experience when they wrote their first parallel program, but for me that was pretty mind-blowing the first time I just changed iter to par iter and it worked. And not only did it work, but I was using it across a file directory that has something like 500,000 photos in it, and it was just, printing out the names or something like that or moving them. It was a simple backup tool that I was building. But I went from sort of multiple seconds of runtime to imperceivable amounts of runtime. It's just mind-blowing that that's not more widely leveraged and more widely appreciated. I suspect the Rust incumbents, the people who are really diehard about Rust, are out there because Rayon is a hugely popular crate, and so is Crossbeam and some of the others that it's built on. And obviously Tokyo is huge, which probably aligns more with what you were saying earlier about the architecture might do more blocking in the future. But yes, specifically maybe we should move back to the JSON thing for a moment, because there's a very, very, very popular crate that I'm thinking of that I won't say the name of for the moment that's used in Rust for serializing and deserializing JSON. It is able to do so in an incredibly performant manner as a result of Rust's type system. And that's probably the last thing about Rust we haven't talked much about, the type system. How much did you guys leverage that in your implementation of RedisJSON 2?
Take a look at the GitHub code base. If you're interested in the details, I'm almost tempted to say. No, I mean, as I said, this is the reason why we spend an awful lot of time in getting the SDK layer right. Because everything that runs on top of the SDK is type safe. As far as I know, you don't have any unsafe code blocks in your RedisJSON 2 implementation and other implementations that are forthcoming of modules in Rust. This is the reason why so much effort went into properly designing the SDK codebase and minimizing the overall impact in terms of unsafe code blocks and also performance overhead, goes without saying, inside the crate, because every microsecond that you spend in the SDK doing superfluous tasks that could have been either done on the server side or on your maybe parallelized module, you're spending too much. And this is the reason why the SDK crate also doesn't tend to be in beast in terms of complexity and lines of code, because it's similar to Redis, minimal in implementation, but designed properly and engineered thoroughly because of these reasons. Because everything that is relying on the SDK shouldn't contain unsafe code blocks.
Yeah, well, I mean, there shouldn't be any unsafe code in an ideal world, but we can be more realistic as opposed to less idealistic when it comes to that, I think, given the state of things. Great. So I want to be respectful of your time, obviously, and we're probably running up against it here, but I will throw a link to your podcast and your FOSDEM talk and the GitHub, as mentioned earlier, in our show notes and things like that. But before we wrap up specifically talking about Rust, I want to ask you two purely opinion questions, which are, what's your Linux distro of choice, and what editor do you use when you're working in the best programming language in the universe, Rust?
I'm almost sounding probably a little bit biased here. Full disclosure, I'm an Arch package maintainer. All the ARM cores that don't run Android run actually Alarm, which is Arch Linux for ARM. On the other machines, I use Ubuntu, Debian, Fedora, and CentOS.
All of the big ones.
So it's a mixture of many distributions of choice. But I reckon I'm not kind of disclosing any secrets here. For the production ARM cores and for the playground Intel-based, I'm using Arch. And the editor of choice, it's tricky. It basically depends on the project at hand. Full disclosure, apart from Rust, I do use other programming languages too. So sometimes it's PyCharm, sometimes it's IntelliJ. But if I program in Rust, if I'm doing this in an embedded fashion, I would resort to Emacs, because Emacs runs everywhere. And if it's as small as a Shiva plug or something comparable, if I'm working on a full-blown GUI like Ubuntu, like CentOS, like Fedora, I reckon the editor of choice would be a Visual Studio Code, because the language integration, even going beyond RLS, which I think is the next big thing for the community, is just excellent.
I couldn't agree more. Well done. Excellent. Cool. Is there anything else we should have talked about? It's interesting just now that you mentioned the ARM processors, actually. I guess you must be pretty stoked about Apple's most recent news that they're going to be...
A14, yes.
Design. Yeah, I can, it's been a long time coming.
It's a fun fact, but not that many people know that actually Apple now is coming back full circle, because the PowerPCs, as coming from IBM, that was the latest rage before Intel, were actually RISC architectures. Not necessarily ARM-based ones like the A14 that Apple is currently targeting the new generation of Macs with, but rather something coming from IBM having its origins in something called ROMP 802. You're going back to the 70s now, because Intel was, IBM was probably the first company to take a serious look at what can be done with regards to reducing the instruction set.
Yeah, I'm not sure if it was IBM and those guys at Berkeley, David Patterson, really, that kicked RISC off. And at the time, everybody was laughing at them, thinking they were idiots, right?
That's exactly it, yeah. ROMP, actually, I don't know if you know about the 801 project. I can't even remember the name, but somebody in New York State took a very serious look at the typical usage of IBM 370 assembler instructions and came up with the conclusion that your ordinary app stack, like COBOL or IMS or other application stacks at the time, would only use 15 to 20% of the overall code base. Hence this idea of doing it better and doing it faster. And hence 801 was born, I think, in 1975 or something. It's all on Wikipedia, people. Look it up. One final plug, if I can squeeze in a shameless plug.
Squeeze all of the plugs in.
There is, of course, the FOSDEM talk. There is Redis.io. There is also the community page on Redislabs.com. Just Google for it with the documentation of all the modules. You find the code base on GitHub. And yes, I run a podcast, not Redis related, linuxinlaws.eu. Yes, so for a little bit of fun, for a little bit of comedy, because I reckon it would be the first podcast rather, that mingles or that combines humor and open source in a kind of hopefully big way. Go to linuxinlaws.eu. I've just uploaded the 11th episode yesterday of season number 1. So we have been around for the last 4 months, I think. But I think we have now a steady listenership of at least 5.5 people, if not 6.
Okay. I'll put a link to that in the show notes as well.
Hopefully this plug changes this in a better way. Check it out, guys. It's linuxinlaws.eu. Links in the show.
Okay. All right. In that case, thank you everybody for listening. Thank you, Chris, very, very, very much for coming on and having an interesting talk. I certainly learned a lot because this is not anything at all related to my area of expertise, but I'm sure this is an area and a domain space that Rust can definitely have a strong hand in the future. So hopefully everybody enjoyed listening, and we'll catch you all next time. Thanks very much, Christoph.
Thank you for having me. Take care.